After deriving the formula for the DFT, such that x of r is given by a formula that can be computed on a computer, we will now look into how this formula can be implemented. One of the quickest and easiest ways is to use for loops, where the first for loop goes through the discrete frequencies r, and for each discrete frequency r, the second or inner for loop calculates the sum for k equals 0 to n minus 1. However, from a numerical perspective, this is very inefficient. Another option to implement the DFT is to choose the matrix vector format. To see this, first write out the expressions for x of r. Here we have chosen m equals n for simplicity. Then the vector containing the DFTs, x of r, is equal to the multiplication of a matrix A containing complex exponentials and the vector containing the samples in the time domain. This method is still relatively inefficient as it requires roughly n squared arithmetic operations. A group of very efficient implementations of the DFT are called the fast Fourier transform, or in short, FFT. It is important to remember here that not only one FFT exists. There exist several efficient algorithms that are all called FFT. Also, despite the name fast Fourier transform, the FFT is not a new or different transform. It is only an efficient way to implement the DFT. Here we will focus on the radix 2 method. As the first step to understand how this FFT is working, we will separate the sum to calculate x of r into even values of k and odd values of k, where we assume again that n is equal to m and that n this time is even. Next, we will define two new signals. G of k contains all even samples of x and h of k contains all odd samples of x. Then x of r is equal to the DFT of the even signals g of k plus the DFT of the odd samples h of k, which is multiplied with the so-called twiddle factor. This procedure can now be continued as long as the number of summons in each sum is even. And if the number of samples n is chosen to be a power of 2, this can be done until the last sums only contain 2 terms. Then, as the last step, all terms have to be multiplied with their twiddle factors and added. In case the number of samples is not equal to a power of 2, the remaining samples to reach the next higher power of 2 are simply filled with zeros. This way, only 5n times the logarithm of base 2 of n arithmetic operations are required. Hence, this calculation is much more efficient than using a for loop or matrix and vector formulations.